Hi, thank you so much for having me. I've really enjoyed getting to be a fly on the wall over the last, I don't know how long it was, over the last 30, 40 minutes. Great messaging, what a great atmosphere in the people gathered here today. Very uplifting. Hopefully I don't spoil it with too much nerdiness in the midst of all of this good feeling and supportiveness. And I definitely want to honor all of your schedules. So I'm going to go through this pretty quickly. It can be kind of heavy material, but I'm going to do it to try to get it done in 20 minutes. But I want to give you guys the most important messages here. So let me pull up my PowerPoint, wherever that is. Okay, and let me know if the sharing is working in a second. Okay, hopefully you can see my slides. Yes.
You are good to go.
Okay, great. So, I'm going to give a quick overview on what we call the most common dysfunctions of the standard American gut. Virtually every major chronic illness, and when I say major, I mean it's the chronic illnesses that account for 80+% of fatalities and morbidity in the US. Virtually all of them are driven by gut and immune dysfunctions. And the immune dysfunctions comes as a secondary effect of the gut dysfunctions. So with that in mind, we really want to look at what are all of the common underlying factors in all of those dysfunctions. And it becomes really relevant right now with this pandemic, with this COVID-19. And so I added in this little illumination from COVID-19 because at the end of the day, our biggest protection against COVID-19 is going to be our immune system, and is our immune system and the resilience of our immune system. But so much of our immune system is dictated by our systemic health and our gut health. And so I want to illustrate that for you to some degree as well. And also make the note that everything you guys do right now, and typically, your work is focused on total wellness and managing chronic illnesses and so on. But all of that work, everything that you do to achieve those results, is completely relevant when it comes to this particular infection, this particular pandemic as well. So even though you're not necessarily frontline healthcare workers at the hospitals working on very sick patients, everything you do is incredibly relevant and incredibly important, because everything you do leads to resilience in the system, which will help us naturally fight this thing and build the immunity that we need to build. So keep that in mind, and I hope this information will help you really put those pieces together as why your job is so important in all of this. So just to give you a quick overview on the virus itself, it's an envelope virus. And as you know, viruses can be envelope or capsid virus. Envelope viruses are made up of a fatty acid envelope, which is a good thing for us because that makes this virus a little bit more susceptible to things like UV radiation and cleaning solutions and heat and so on. So it's not that robust of a virus when you look at it in the context of other viruses. Capsid viruses, ones that have protein coatings, tend to be a little bit more robust. This is a RNA virus, a positive sense RNA virus, which means that once it attacks a cell and gets into the cell, it squirts in its RNA, takes over the ribosome of the cell immediately, and the cell immediately starts making viral proteins. As you guys know, viruses are amazing hijack artists. And they can't do anything for themselves. They're not even living organisms, actually, technically, because they have no metabolic capability. They have no way of replicating themselves. They have no way of creating any sort of energy at all. They're just actually biologically floating bags of DNA or RNA. But their whole trick is they have receptors on their outer membrane that find very specific receptors within the host. In the case of the coronavirus, they find the ACE2 receptor. Now, this evolution of the virus makes it a major problem for us because the ACE2 receptor is a receptor that is pretty ubiquitous in the human system. ACE2 is a really, really important protein, which I'll talk about in a second, but it's a transmembrane enzyme, so it's a transmembrane protein. It sits on the membrane of numerous classes of cells in our body, and it's there as part of our really important repair mechanism. Because it's ubiquitous, it then gives the virus a number of targets when the virus enters your system. And then the ACE2 also is a signal that that cell or that tissue is undergoing some sort of damage or stress. So it's a way not only for the virus to use a ubiquitous receptor, so it has lots of ways of entering into cells of the body, but it's also a signal to the virus that this cell in particular is undergoing some sort of stress. So let me give you a quick review on ACE and ACE2. ACE falls under something called the angiotensin-renin system and pathway. Angiotensin is an enzyme that can conduct lots of different functions within at the cellular level in the body. ACE and ACE2 compete for angiotensin. When ACE converts angiotensin into angiotensin 2, what you end up getting is a net effect of increasing reactive oxygen species, because part of why ACE gets expressed is because there is some sort of damage or abrasion going on in that part of the tissue. So it's going to increase ROS as an antimicrobial type of response. It's going to increase inflammation, which then is in an attempt to sequester that area so that anything that's invading in that area can't get out. Just like if you get a cut on your skin, you see the area and around it gets red and inflamed. That's a sequestering, quarantining technique that your body does. It reduces blood flow, so it does create vasoconstriction because it doesn't want things from that damaged site to escape into the rest of the body. It does increase apoptosis, so this faster cell death and turnover. And in the case of the pancreas, it actually reduces islet cell proliferation. In the case of the kidney, it does reduce proliferation of the kidney cells itself temporarily. So it's an important part of the repair mechanism. The problem is if the ACE-like effect is allowed to go on for too long, you actually lose compliance and function of that organ or that tissue. So the counteracting force to ACE is the ACE2 system. So once ACE gets expressed and repair starts to happen in a damaged tissue, ACE2 follows and starts competing for angiotensin, and it sends angiotensin down a different pathway called the MAS pathway. The MAS pathway leads to opposite effects of the ACE and RAS pathway, and that is decreasing reactive oxygen species, decreasing inflammation, getting the blood flow back up, reducing the apoptosis, and increasing the proliferation of those target cells. So ACE2 is incredibly important because what tends to happen if you get too much ACE activation and not enough ACE2, you get too much repair and you get over repair. You get things like hypertrophy that occur. You get things like fibrosis that occurs. You get fibrosis in the vessels, for example, and then you start to lose the compliance to the vessels. And then ACE2 has to come along and stop that over repairing process. So it's counteracting systems. For example, if you end up with cerebral ischemia for whatever reason, then the ACE type of response will lead to neuroinflammation, oxidative stress, and then eventually neural apoptosis, which leads to brain damage. Now, the ACE response is required early on for a very short period of time to get things sequestered and under a repair state, but then ACE2 has to come along to undo some of that overactivity and actually lead to less brain damage and more compliance. This is most well known in the heart, and this is where ACE inhibitors come in. So when you have high blood pressure, when you have high blood sugar levels, in the case of diabetics, when the ventricles are pumping blood, they're pumping more abrasive blood, they're pumping it under higher pressure. And so the muscles around the ventricles, these smooth muscle cells, actually get damaged over time. So they're undergoing constant damage and inflammation. And so ACE is continuously expressed in these tissues. And when it is continuously expressed, and if ACE is left to go unchecked, then you end up getting a hypertrophy in these muscles. just exactly the same as on your skeletal muscles. If you lift with your biceps, if you do a bunch of curls and you damage and tear those muscles, you're going to get an ACE-based repair on those muscles, and the result is a hypertrophy or increasing in the volume and the size of those muscles, which in your skeletal muscles, that's a good thing. You feel good about yourself. But when it happens in the heart, the problem is you shrink the chambers of the heart and you shrink the flexibility of this vessel, of this organ as well. Just like if you lift too much and you get too much hypertrophy, you actually should reduce function and flexibility in your skeletal muscles as well. This is why they invented ACE inhibitors, because ACE inhibitors block the function of ACE1 and allow ACE2 to be more expressed to prevent this type of hypertrophy. This type of hypertrophy can lead to cardiovascular disease. So this is the battle between ACE and ACE2. And ACE2 happens to be the receptor that the virus targets, but ACE2 is expressed in damaged tissue, and it indicates in the body damage, and it indicates susceptibility of the tissue because the tissue is undergoing damage and remodeling. ACE2 is triggered by inflammation, by systemic inflammation in this case, and also by malnutrition in the gut. So you get ACE2 expression in the gut because of malnutrition and poor diets, and then you don't get the function of ACE2, which is trying to repair the gut lining. So you get a double whammy. You get more expression of ACE2, but you also don't get the repair function of ACE2. Now, remember, in COVID-19, at least 53% of the patients are experiencing GI symptoms first. And there's some indication that people with GI symptoms first actually end up having worse conditions with COVID-19. So having an adequate gut health is going to be incredibly important, and the systemic inflammation that drives the expression of ACE2 increases people's risk factors. Another thing that really drives ACE2 expression in numerous tissues in the body, which again, if you have more ACE2 being expressed, you have more targets for the virus, is the presence of lipopolysaccharide, or LPS. This LPS and lipopolysaccharide comes from the gut. So when your gut is leaky and LPS is allowed to leak into the circulation, it's going to end up in various tissues in the body, including in the lungs. And in all of those tissues, including in the lungs, it can generate an expression of ACE2 because ACE2 shows up to try to help with the repair that's going on in the system. And we see, this whole idea of acute respiratory distress syndrome, which is what is driving most of the mortality, or what is thought to drive most of the mortality with COVID-19, is an inflammatory process by the body. So you've got the immune system overreacting to the presence of the pathogen itself. And it's no surprise that people with all of these chronic conditions are the ones that are succumbing to this pandemic and virus at a higher rate than non-chronic ill subjects, and all of these chronic illnesses that create significant risk are actually being driven by chronic low-grade inflammation. So that's the overarching message there. I know I said a lot, but I think the important message I want you guys to take away from that is the resilience against this particular pathogen is going to come from having less low-grade chronic inflammation, less tissue damage going on inside the body, less expression of ACE2, and a better functioning immune system. And that part of the immune system that's absolutely critical to deal with a virus like this is the adaptive part of the immune system, the antibody-producing part of the immune system that involves T helper cells and B cells. And all of that gets dysfunctional when your gut is dysfunctional, which I'll talk about here, and how those dysfunctions occur, right? So this is your normal gut schematic. If any of you have seen me talk over the last year and a half, you might have seen this already, but the important part to note are some basic structures. This is the mucin layer that sits on top of the intestinal epithelium. The mucin layer has two distinct layers in it, the mucin 1 layer and the mucin 2 layer. The mucin 1 layer is a more liquid, less rigid part of the mucin layer, and most of the microbiome exists in that top mucin 1 layer. Mucin 2 layer I call the inner sanctum because it's the layer that's closest to the intestinal epithelium and all of the immune cells in the intestinal epithelium. And that layer is supposed to be relatively sterile. You're not supposed to have a lot of your commensal bacteria in that layer, because if you do, the immune system in the intestinal epithelium tends to freak out, and everything gets an inflammatory response because your body is anticipating a flood of microbes entering the system, because once you go past this intestinal lining, you're entering the basolateral circulation. So you're effectively in the body, in the circulation, right? So this barrier system is the last layer of protection of things from being from outside of the body to inside of the body. Once things are allowed to flood through here and possibly enter through in between the gaps between these cells, it causes a significant amount of dysfunction and immune inflammatory response. So the keys to maintaining homeostasis in this particular structure is high diversity within the microbiome. Diversity is absolutely paramount, and diversity is driven by lots of things you guys were already talking about. High diversity in plant-based foods is absolutely critical. The vast majority of beneficial protective strains in our microbiome require and like plant-based foods. High diversity in polyphenols, flavonoid intake, carotenoid intake, which comes from colored fruits and vegetables. Those things all serve to increase diversity within the microbiome, and also serve to increase the relative abundance of certain protective strains, which I'll talk about in a second. You also need high production of short-chain fatty acids, which I'll talk about where that comes from. And then, of course, well-formed tight junctions as well. There's about 40 different proteins in between these cells that create the tight junctions. So what tends to go wrong in this whole system? It starts with this process of dysbiosis, right? And how do you define dysbiosis? You all know what this term means, but the way you define it is first by having a reduction of keystone strains. Keystone strains are highly protective strains in the gut. Many of these strains have been shown to be inversely correlated with a large number of chronic illnesses. Strains like Akkermansia muciniphila, Faecalibacterium prausnitzii, Bifidobacterium longum, Bifidobacterium adolescentes. These strains are directly connected with health and wellness, and in part because they maintain structure within the rest of the microbiome, and they do lots of critical things to maintain this structure and this type of immune response, right? This type of favorable immune response. Let me make one more note on this homeostatic side. Another really important function of this inner sanctum of the mucin layer is that's where most of the immune sampling occurs in the body, right? That's where the immune system learns about the world around it. So anytime food particles or virus particles or toxins or bacteria components migrate through here slowly, it gives a chance to the immune system to react to it. The intestinal epithelium will recruit immune cells to it. The immune cells will examine it. The antigen presenting cells will present it as an antigen. Then the immune tissue in the intestinal epithelium will get to decide, is this something we need to attack and go after, or is it something we need to build tolerance to? Now, interesting in that conversation of figuring out whether we build tolerance to something or we attack something is the microbiome. The microbiome has really intimate crosstalk with these immune cells, which effectively helps tell the immune cells that this thing is something you need to pay attention to, or this is something that you need to build tolerance against. So remember, the microbiome sees it first, and then as it passes through the microbiome, it can get tagged with signals from the microbiome, and in fact, in some cases, actually get presented to the immune tissue by bacteria within the microbiome with the right context. So your immune system gets to learn about the things that are entering your system and about the things that you typically tend to be surrounded by. So this is called immune crosstalk, and that immune crosstalk is absolutely critical for your immune system to function appropriately. If not, your immune system tends to attack everything with an inflammatory response, right? So I wanted to make that as a caveat because I forgot to mention that earlier, because it becomes really important when you start to see things go awry right here. So you have low levels of keystone strains of the first part of dysbiosis. The moment you have low levels of keystone strains, you'll start to shrink in diversity of bacteria, because many of these keystone bacteria actually promote and maintain diversity. Then you start having lower levels of certain postbiotics that are really important to maintaining this whole system, things like short chain fatty acids like butyrate, propionate, and acetate. The moment you start having this situation, then what you start to get is an aberrant growth of dysbiotic bacteria that will eat away at this mucin layer. When they start eating away at this inner sanctum mucin layer, you start to get a net translocation of all of the bacteria, viruses, food particles, toxins, and so on that exist in this upper part into the lower inner sanctum area. And I call it a sanctum because when these things start to enter this area that they're not supposed to be in large volume, it causes the immune system to freak out. And then the inflammatory part of the mucosal part of the immune system, which does all of the sampling, actually starts to create inflammatory responses, not only in the gut, but that inflammatory response is translated to the rest of the body as well, right? So that is really important to note, that a disrupted mucosal immune response is at the heart, is at the root cause of all chronic illnesses. It's at the root cause of disrupted function of the immune system itself. So I'll leave it at that. This is why gut health is so important for everybody to keep in mind. And everything you guys talk about in terms of improving the gut and so on plays a really important role in correcting that system. So Andrea, I think you probably have to break. So I will stop there.
Actually, Kiran, we would love to ask you a few questions.
Oh, sure. Okay.
This is Christy. A lot of this information might be over some of our heads. So I'm gonna ask you some questions. Just break it down as if we're all 4th and 5th graders.
Okay. Yeah.
Awesome. And I do know that I have some food in my teeth. I just saw that. So to get, I was eating my greens. Can you explain lipopolysaccharides? What are some of the foods that contribute to that toxin?
Yeah, so lipopolysaccharides are actually made by bacteria. These are transmembrane fatty acids that are found in the membrane of gram-negative bacteria. So every bacteria in the world can be categorized as gram-negative or gram-positive, right? Gram-positive means it has a cell wall on the outside. Gram-negative means it doesn't have a cell wall. It has a cell membrane, which is a fatty acid membrane. Now, in that membrane is another fatty acid called lipopolysaccharide, this endotoxin. It is the most pervasive and toxigenic endotoxin. Bacteria produce it from fat that comes into your from your diet. Now, what's interesting is that the bacteria, when they're producing their lipopolysaccharide, which is they produce it for their own use. They use it for numerous things, but they produce a more toxigenic version when they do it with saturated fats. That's part of the connection why saturated fats can have much more of an inflammatory effect in the body, because when they produce it with omega-3 fatty acids or omega-6 fatty acids, it's less toxigenic. When they're producing it with saturated fats, it's a more toxigenic lipopolysaccharide. So that's where the diet can influence. And then also, if your diet tends to be really high in fat, when the LPS is released into the lumen of the intestine, you'll end up inadvertently bringing more of it into the body, because in order for your body to deal with and digest lots of fat in the diet, your body produces lipid rafts or chylomicrons that go across into the lumen, pull the fat into the body. Because LPS is a fatty acid, it's going to accidentally pull in all those toxins as well. So those are two factors. When you're eating really high fat diet, you're going to bring in more LPS. And when you're eating high in saturated fat, you're going to make a more toxigenic version of LPS.
Wow. So here's the good news, everyone. This this has been recorded, so we can all go in and dig in a little bit more and learn more about the microbiome. Kiran, this has been amazing. Will you please put your information in the chat? Because I bet people are going to have questions,
Sure.
Especially a lot of our practitioners and doctors and providers, and that way they can get a hold of you. And then we are going to cut to lunch. It's so good to see everyone here. So just like Kiran gave us all this information to digest and soak up and emulate in our lives, go choose some healthy foods, have fun at lunch. We're going to come back with a huge amount of glory. We're going to continue this joyride, and we got amazing people. So eat up, digest, assimilate, and come back for this joyride.